Okay, so this is going to be the pre-lab video as well as kind of like the data video for our experiment about atomic absorption, right? Now, atomic absorption is an instrument lab that we would have been doing where we could actually measure the amount of calcium inside of a sample of milk. Unfortunately, this isn't something that we're going to be able to do remotely. And while I've been able to find some videos that showcase it, I didn't find the great simulation that I really liked. And so we're kind of going to do a combination of me providing you with data, and then there's also some links to the instrumentation so you can kind of see what that looks like. So on our module page, this video is going to be what's posted here, and so we should be starting with that. What I want you to do is go ahead and open up this document here, Atomic Absorption Theory, as well as this data sheet. Now, this lab isn't inside your experiment, so you're going to be filling out this data sheet as you go through. So the first one, the theory part, is this PDF. It's about 3 pages long, and is breaking it down there for us about what atomic absorption is. And so the idea behind atomic absorption is that we're going to release some energy. We're going to excite our atoms of a specific element. That energy is going to flow in. It's going to excite those elements. When those elements are excited, then they're going to absorb in energy of that wavelength. Right? Now, each element has specific energy gaps from their ground state to their excited states, similar to what we saw with the emission spectra. The absorption spectra is something similar. The difference is that they are absorbing photons to move up. And so for this to work out, they have to have the ability to absorb a photon of that energy. So they have to have a gap that corresponds with that energy difference. So we're looking at atomic absorption. So we're going to use a lamp that gives off a very specific wavelength for calcium. It's going to shine this calcium light, basically. That's going to ionize our sample, or sorry, that's going to flow through our sample, and then we're going to be able to measure how much of that light is absorbed. Now, we're doing something called flame absorption spectroscopy, in which case, what's going to happen is we're going to input our sample into a flame, and that flame is going to break apart all of our compounds. So like all of the calcium, the material inside of the milk is going to turn them into atoms of calcium. So we're going to kind of break apart all those compounds, so that way we can get the free calcium, and that way we can measure how much calcium there is to be absorbed. Now we are going to measure the absorbance of something, right? So the absorbance of something is kind of like the inverse of the transmittance, right? What that means is that when we shine a light, if all of the light makes it through, then that would be 100% transmittance. That means all of our light was transmitted to the other side. Absorbance is going to be 0% because that means none of the light was absorbed. So the more light that makes it through, the higher the transmittance and the lower the absorbance. The more light that gets picked up, the higher the absorbance is going to be. And so we're going to measure the absorbance. Basically, we're going to shine our light through. We'll see how much light is coming through when there's no sample. We'll put our sample in, and we can tell that difference in terms of absorbance, and that's going to be related to the concentration according to Beer's law. So we're going to use that to create a standard calibration curve for our material. We're going to be able to measure at different concentrations how much calcium, for different concentrations of calcium, how much light was absorbed. And then we're going to use an unknown sample of our milk. We'll measure its absorbance, and we'll be able to backtrack that to its calcium. And so that's kind of like our background information of what that looks like. Now, there is a more in-depth video here that kind of goes through that theory of it, and so you can watch him as well. There's also a short video where they're showing you the instrumentation. So if you're a little bit lost about the diagrams and the pictures, then look at this one. This one talks a little bit more about the background about why atomic absorption works. Right? It's a little bit in depth and detail, but I do think it is a good watch. It's only about 4 minutes long. Okay? So our lab is going to look like this document down here, the data sheet. So this is what we're going to try to fill in. It's only 2 pages long. And so the first part is we're going to prepare these solutions of our calcium standard, and our unknown sample. And then part 3 is where we're going to collect that data. So right now I'm going to walk through with you how you fill in table 1 as you fill in the standard solution. So when we're looking at our standard solutions, we're going to do what we call a serial dilution. So we're taking a flask that has our solution, which is going to be 100 milligrams per liter. That's the concentration of it. And so what that is saying is that there's 100 milligrams of calcium in 1 liter of solution. Now, when we do our, so we're also going to make a solution that's going to be 10 milligrams per milliliter. We're going to make another one that's going to be 5 milligrams per liter. And we're going to make a third one that's just 1.00 milligrams per liter. Now, as we go through this, we're going to take some, well, this one we're going to measure as solution 1. This will be solution 2, solution 3, and solution 4. Now, when we make solution 2, we're going to get that from solution 1. So the first part of what we want to do is we want to measure out how much volume we need of our sample versus how much volume of deionized water we're going to add to it. So when we look at our table here, when we look over at this table down here, for solution 1, if we want to make a total volume of 10 milliliters, we want to figure out what volume we need to put in for each. So if this is 100 milligrams per liter, we don't need to change anything here. That's what we want. So we're going to put 10 milliliters of our calcium standard here, no deionized water. Then, when we move on to our second part, we're going to have to dilute that. So let's go back to our whiteboard. So this one here is 10.0 milliliters of calcium, 0.0 milliliters of water. So if we want to go to 10.0 milligrams per liter, we have to make an adjustment there. We have to make it more dilute. So what we want to do is we want to take the calcium from solution 1 and set that equal to the calcium in solution 2, because they're going to be coming from different volumes. And so this is where we can use our concentration of our calcium times the volume that we need to transfer from solution 1 should be equal to the concentration of our calcium in solution 2 versus the volume of its sample. So we have 100 milliliters of solution 2 that we want to make. That's the total volume of the solution. And we know the concentration is 10.0 milligrams per liter. That's coming from an 100.0 milligram per liter calcium solution, and we don't know what volume we need to transfer. So we want to solve for the volume being transferred. And so that becomes 100 times 10, so 1,000. We divide that by 100. So 1,000 divided by 100. And we find out that we should transfer 10.0 milliliters of solution 1. That will give us the calcium that we need. Once we transfer that 10.0 milliliters of solution 1, then we need to figure out how much deionized water we need. And so if we're trying to make something that's 100 milliliters, we subtract how much of it was solution 1. So that becomes 90.0 milliliters of DI water. Now you would do the same thing for solution 3. For solution 3, we would have the concentration of calcium in number 2 times the volume that it needs to transfer. We'd have the concentration of calcium in solution 3 and its volume, which is 50.0 milligrams. So we can plug that in as 5.0, 50.0 milliliters. And this is going to be 10.0 milligrams per liter. And we should be able to figure out what volume we need to transfer. And so you're going to complete that for number 1, number 2, number 3, and number 4. And so this is how you complete table 1 of your chart. Table 2 is something similar, but our dilutions are going to be different. For table 2, we're going to have this is solution number 5, and this is going to be our milk sample. Now, our milk sample, we're going to go ahead and leave it in its initial state. So if our total volume is 5 milliliters, then we need 5.0 milliliters of milk and 0 milliliters of water. Now on this next part, it's a little bit different. This time, when we move into our next solution, instead of giving us our concentrations as a number, since we don't know those concentrations, they're given to us in the term of a dilution factor. And so what that tells us is that when we get into solution 6, we know that solution 6 should be 1 to 100 compared to that of solution 5. Now what that means is that if we imagined our flask is this giant container, 1 to 100 would mean that if we put 1 milliliter of our solution 5, so of our milk, the rest of this would have to be water. And that comparison would be 1 milliliter of water to a total volume of 100 milliliters. So for making solution 6 is just going to be 1 milliliter of solution 5. And if we want to make the total volume 100, then we need 99 milliliters of water. When we go to make solution number 7, sorry, that is a terrible flask. Then solution number 7 is going to be a 1 to 200 dilution. So that's going to be a little bit different. That 1 to 200 is 1 milliliter of milk to 200 milliliters of solution, which is a little bit hard for us to do starting from the milk. So instead of starting from the milk, we're going to start from solution number 6. We're going to start from the already diluted one. So for that 1 to 100, we don't have to do it 100 times less. 1 to 100 to 1 to 200 is a change of 1 to 2. And so that means that in our total container, half of that total volume should be solution 6. And then the other half should be your deionized water. And so you can use that in order to do your calculations for your preparation for table number 2. So dilution factor is what's a little bit different for this one. And so you just want to think about what the numbers are saying. And so it's always comparing your original amount to your total amount. And so you can use that to fill in those next 2 parts. Now, for our last part, we're going to measure these values and we're going to collect these absorbances. So we're looking over at part 3. So we're looking at this collected data. Now, to get you this collected data, when you look on this experiment page in the lab data provided, when you click that, you're going to see a spreadsheet that looks a little bit like this. And so I've given you the absorbances here in the blue. So for our data sheet, we should be able to fill in our concentrations for solution 1, solution 2, solution 3, solution 4, and we should be able to measure their absorbances. Now, when we did this, we would have measured them actually backwards. We start with the lowest concentrated solution first and then move our way up, and then we do our sample last. But it doesn't matter since we've collected that data. And so I've plotted that here. So you're going to have to create your own graph. Right? Don't use the one that's here because A, you don't actually know what the values are, right? And B, I've actually plotted this as a different trend line, right? So it will be close, but it is not going to be right. So you don't want to use my graph. You want to create your own. And so that's what it's talking about how you create your own graph for your lab write-up. Now, I'm not going to collect your graph since I can't see it, but I do want you to plot a graph. And so you guys want to use your spreadsheet, make a copy of it, so that way you guys can create your own graph here. Now, once you've created your graph, what you're going to be looking at is we have a trend line for this absorbance. So we want to plot it through, we want to add in that trend line. Once we've added in that trend line, we want to use its equation to look at our unknown. So solution number 7 is our milk. These other 4, the ones in blue, are our standards. So we're going to use these blue standards to estimate what concentration our unknown should be. So I've given you the concentration of our unknown, and I've given you the concentration of our standards, and so we're going to be able to use that to find our concentration here. So we'll plot it, we'll find the trend line equation. Once we have the trend line equation, then we can find the concentration of our solution number 7. So let's say that the concentration of solution 7, that we need to figure that out. And I'm just going to give you an equation. Let's say that this is y is 75.2 times x, which is our concentration, plus 0.067. So our absorbance was 0.096, so that's my x. I'm going to use that to find my y value. Now, don't use this equation because it's not going to be correct for yours. You want to use the equation from your graph. And so for our y, we would get 7.2862, which is our concentration in milligrams per liter. And so when we go back and we look at our graph, you can kind of see that 0.096 should be between solution 2 and solution 3. So it makes sense that our concentration is between 10 and 5. So this is our concentration of solution 7. But what we really want to know is we want to know the calcium in the undiluted solution. So if solution 7 is 7.2862 and we have a 1 to 200 dilution, that means that our sample should be 200 times more concentrated in the undiluted. So we'll take that 7.2862 milligrams per liter. We'll multiply it by our 200 to 1, because this is our undiluted. And so we had a concentration of 14,057.24 milligrams per liter. And that's how you can go through and do your concentration. Now, you want to go and finish the other 3 questions. So you want to tell me what your what atomic absorption process, what it is used for, right? And so one thing that I would recommend for question number 2 is that if you don't have an equation in there, it means that you're probably missing something. So look for your equation that ties in absorbance, concentration. And this should be from your theory, not just your trend line equation, but go back to your theory. The other part is, remember that combustion is going to be your C2H2 plus your oxygen. Right? So go back and look at what hydrocarbon, what products they make when they go through combustion. I'll give you a hint that it has to deal with carbon dioxide, right? So look through that one. And then the last part is we're looking at number 4. Now, 1 ppm is equal to 1 part per million. What that means is that you would have a fraction of 1 over a million is a ppm. And so we're trying to show how 1 milligram per liter, how is that related to 1 ppm solution of 1 gram per milliliter? So compare 1 milligram per 1 liter. Sorry, I shouldn't use an equal sign there. We should compare to 1 gram per 1 milliliter and see what that looks like. All right. Let me know if you have any other questions. Good luck.